Okay, so I can't pull up the announcement. Actually, yes, I can. Right. So I talked about how 60% of all ICPC problems can be reduced to some graph problem. And it is essential that we learn the tools to solve these graph problems. And of the kinds of graph problems that exist, the shortest path are the most common. So we're going to be going over some of the more, well, we're not going to be going over any of the stuff that you would have learned in 330 because that's part of the reading from before. And also, um, those algorithms, we don't have enough time to go over all of that plus the new stuff. So I just assigned that as reading, and we're going to be going over, as what I'm about to show you is something called a 0-1 BFS. What's up? I mean, I don't. If you guys can see, can you see, or are you bothered by the sun? I, if you can't see, then let's.
How many CS majors does it take to close a book line?
Too many. Where is the? This one does not have a. Maybe it just pulls. No. That seems to be this is the one that's. Oh no, this one is not exact on that. That's the one that's actually loud.
If it's not working, I could just move.
Oh. Is it stuck?
Yeah, I'm stuck. That's what
It's changed.
it is.
Yeah. Lucas.
There's like, no.
Are you a student here, by the way?
Yeah.
Are you a postgraduate?
Right here, it's not why it's like that. Do you do all of it?
Sorry?
Don't you do all of it? Like you're just,
Yeah, I study a lot.
Like,
Oh man.
you gotta I know how you work.
I'm serious about this.
You gotta alternate for the day. Yeah, that was the problem.
Okay, let's get started. I mean, Keisha, right, is out of the light, so it doesn't really matter anymore. As long as everybody can see. I mean, okay. So, what is the 0-1 BFS? Before I play the animation, I want to explain. So, does everybody like know or remember Dijkstra's algorithm?
Yeah.
Dijkstra's algorithm is basically a BFS, right? So a BFS, breadth first search, right? You go, instead of going depth first down a graph where you just chain nodes recursively, breadth first search goes layer by layer down the graph. That's like as brief of an explanation I can afford. Dijkstra works for weighted graphs, right? Which have no negative weights, right? So non-negative weighted graphs, Dijkstra's will find you the shortest path. And how does Dijkstra's work? So Dijkstra is a greedy algorithm, and the way that Dijkstra makes sure that it always gives you the right answer is by prioritizing paths that are, to our best knowledge right now, the shortest path from the start. So what that means is like, if I let's say I'm like some way along my breadth first search and I have a fork in the road, and this is, let's say the shortest path from here up until here now, let's say this path was like 10 and this is like 5 for a total of 15, and this one is only 2 for a total of 12. As long as we just greedily pick this one with the lower weight, it will ensure that we arrive at the accurate solution, the shortest path from the source to all nodes. Why? Because think about if we had picked, I shouldn't have. Think about if we had picked the largest one first, right? And we picked 2 here, and let's say we have another 2 here. If we pick this guy first, and then we start going along this way, right? This guy's gonna have a value, this guy's gonna have a value. And when we come back to this guy, and we get here, we realize, oh, okay, well, 15 wasn't actually the shortest path. 2 plus 2 is 4 was actually the shortest path. But now, all the work that we did up here needs to be changed too, right? because we were assuming that it was 15 to this point, and then it was 15 plus A, 15 plus B, but now it's only 4 plus A and 4 plus B. So we have to do extra work to basically undo what we did before. So as long as we prioritize this shortest path first, we will never have to re-update like the descendants of a node in the graph. Now, so that's basically Dijkstra's. But what happens? So in order to Dijkstra's works by maintaining a priority queue, right? A min heap, right? Which basically has a property of whatever's on the top of the heap is going to be the smallest element in the heap. So as long as whenever we do our breadth first search and we're scanning for edges, every time we add a new edge, we make sure that we preserve the heap property so that the minimum element is always the one at the very top, right? And that takes, eventually that'll be n log n in asymptotic notation. It will take n to complete one Dijkstra's pass over the graph. But what if we only have two weights, 0 and 1? This can happen a lot of times where, think of like a door is blocked and you have to use a key, or there isn't a door blocking you and you don't need to use a key, or something like that. Like that's an example of a graph with 0 and 1 weights. And what you can do is, instead of running Dijkstra's, you can run this 0-1 BFS algorithm where, remember, Dijkstra said we need to always prioritize the shortest paths first, which meant we have to maintain a priority queue because we don't know the maximum range of the weights of the edges. But with 0 and 1, we know there's only going to be either 0 weight or 1 weight. So we can apply the same greedy invariant from Dijkstra's, which is basically just, if a weight has 0, explore that weight first. If it has a weight of 1, store it for later until we have no more zeros in our queue, and then we'll unravel all the ones. So let me play the animation, and then we'll talk about it. Now, I didn't have... Oh, so I apologize. I didn't have as much time to make the animation super pretty, but let's go back. Okay. All right, so what's going on here? So here's our graph, and it's got all of its weights. So as you can see, 0 to 1 has weight 0, etc. What we're going to do is we're going to have a double-ended queue. Just remember the double-ended queue from last time. You can also simulate this with 2 stacks. It's basically the same. We basically want a 0 container and a 1 container. And the idea is, if the 0 container is full, take from it. Otherwise, take from the 1, right? So what we're going to do is we're going to enqueue our 0 first. That's just the first node, so that's going to have a weight of 0. Then we're going to travel to 1. As you can see, it got a little bit thicker. We're traveling to 1. So we're going to enqueue 1 with yellow, which is a 0 edge, which means we push to the front of the queue, okay? Now, BFS continues. We traverse to node 3, update its weight, and we push to the back of the queue because it had a weight of 1, right? So as you can see, currently 0 has weight 0, 1 has weight 0, 3 has weight 1, but as you'll see, it's going to get updated. Actually, no, that's a 1 right there. It won't get updated. But the point is, 0's got pushed to the front, 1's got pushed to the back, and we're always going to pop from the front. So you can imagine, if we're always pushing the 0's to the front, or always popping from the front, we're always going to be popping the 0's before the 1's. Okay? 0 weights before the 1 hits. Let's pop that 1 off and start traversing from there. Okay? Now, the 1 is going to get to the 2 with the weight 0, so that gets pushed front. And then 3 is already in it, so we don't re-add it to the queue, but when so that expires, 1 has expired, so we again prioritize the weight of 0, which went to node 2, so we pop 2. We scan its edges, they're both 1, so we're going to add both of those to the back. Okay, now we're going to start from 3. It's got a weight of 0, but we've already visited 4. So what we're going to do is, remember, we're not just traversing, we're updating the weights, right? Now what isn't really visible here is what's going on is, okay, I have at every edge, right? I mean, if you read about Dijkstra's, you already know how this works, but it's called relaxing an edge, where you basically just compare it with whatever the current weight is plus the weight of the edge. So whatever the node has stored, right? The shortest pass to our best knowledge of node 3 is 1, plus a weight of 0. Or if 4 already had a lower weight, then we're obviously going to keep that weight instead. So that's just what relaxing an edge means. So we're going to continue. Pop 4, and then we've already visited everything, but we're updating those weights. And then finally, we get this list. So shortest distance from node 0, 0, 0, 0, 1, 1, 1. Anyways, that's the point. I'm going to structure the lecture a little bit differently because we're not going to go over the code. You can go over the code. It's on the GitHub. But I really want to go over the problems before everybody leaves, because I think that's where the real practice comes from, right? If you know the mechanics, that's one thing. If you know how the algorithms work, that's one thing. But if you can read the problem and be like, okay, I need to do this, then this, then this, that's the actual hard part of ICPC, right? So let's move on to the next idea, which is the Tarjan's articulation points algorithm. So let me give a little bit of a preface first before we start. So, what is an articulation point? Let's say we have a graph like this. Okay? An articulation point is a point where if I remove it from the graph splits into two disconnected components. Okay? So, as you can see, if I were to remove this guy, we have two disjoint graphs. If I were to instead have removed this guy, or perhaps this guy, in either case, we still are left with one graph. There's no two disconnected graphs, right? Why? So why do we care about that? There's a couple of reasons. First of all, imagine you have a network of computers, right? And you want this guy to talk to this guy. Well, he's got to travel through this guy, right? And if this guy's down, then you're screwed. E can't talk to A and A can't talk to E. That's called a single point of failure. And when you're managing network topologies, which boils down to graph problems, you want to avoid these as much as possible. Okay? Another fun example that I thought of for articulation points is, I don't know how many of you guys know what this is, but I used to play a lot of Minecraft Hypixel, and there is this game called TNT Run, where you basically run along TNT where the ground beneath you falls as you're running. Okay? So think about a scenario. Imagine a scenario where the ground is falling underneath your feet as you traverse the graph. Okay? So the nodes are getting deleted as you walk along. Right? If I say, okay, I want the maximum amount of points, so I want to hit every single node. Is that possible if I, for example, start here? All right, let's say that home base is right here. I want to hit all the nodes and then make it back to base. Okay? Well, clearly, if you guys know what an articulation point is, you can see that, hey, this guy's an articulation point, which means that if I want to get to this component of the graph, I have to go through this guy. And if he gets deleted after I traverse, right, we can't go back. So there's no way that we're going to be able to hit all these guys and come back, right? Now, this is actually, a lot of people get confused. I got confused by this original idea where you're saying, can I touch every single node from home base without touching a node twice, right? That's basically what I demonstrated, right? Because if the node's falling out from under you, you can't go back and touch it again. This is different from something called a Hamiltonian cycle, which you might have heard if you took for theory of computation, right? So a Hamiltonian cycle says, can I hit every node in a row from here, let's say from here, can I hit every node and then come back without hitting a node twice, right? So this graph clearly has a Hamiltonian cycle because I can hit every single node and return to home base without touching a node twice. Now, if I go back to the other example, right? Now, there isn't a Hamiltonian path if we start, well, nowhere, but if we start here, right, we can't, there's no way that we can hit all the nodes like such, right? But what the articulation point is asking, or sorry, specifically, not the articulation point, algorithm doesn't ask a question, it just finds the articulation points, but the problem of, can I, let's say I start from here, let's say my home base is here, this is my safe, this is safe, but everything else must, I must be able to hit everything else, right? But I can return to home base as many times as I want. You can actually do that because you can go like this and return to home base, that's safe. And then you can go like this. So you can hit every single node on this graph as long as this is safe, but there is no Hamiltonian cycle. So it's a little bit different. It's actually an easier, more relaxed requirement than the Hamiltonian cycle. So, and the reason I bring up Hamiltonian cycle is because you're never going to see that on ICPC. So if you think, oh, this problem is asking me to find, I need to find a cycle such that I hit every single point only once. That's actually NP hard. So they're not going to ask you to do something NP hard, unless the input size is like less than 10. Anyways, let's take a look at the actual algorithm. So it's a bit long, so I'm just going to go over it step by step. So how do we find, I guess I need to explain one more thing. How do we find this articulation point, right? We're going to be keeping track of two things. Let me pull up the table. So as you can see, we have T in and we have low. What does T in say? T in says, when we do our DFS, record the time that we entered the node, okay? So as you can see, 0 is going to start with a value of 0. What does low mean? Low says, when I reach this vertex in the DFS search, the depth first search, could have gotten to that point faster, earlier, then that's what low is going to be. Low is going to store that earliest point that you could have reached that node.
Sorry, could you repeat that?
Yes, so the whole thing, or?
Just the part about what low means.
Yes, so low is telling you, how, if you could have reached this node earlier, for example, let me just give you an example, right? So let's say the DFS goes from 0 to 1, 0 to 4, or 1 to 4, 4 to 5, 4 to 3. So that's what will be 1, 2, 3, 4. So the time for entry would be 3 or 4 for node 3. But let's say we do that, and then we go back and we hit 1, and then we get to 3 directly from 1, right? So now we've hit 3 twice, once from going all the way around this loop and one from going directly to it. And so we will take the lower of those two values. That's why it's called low. Make sense?
So we would take 5 instead of taking.
Low, if I, okay, if it needs a little bit more context to explain. So,
Oh, I might just want to.
yeah, yeah. So, think about like for any um node on the graph. Let me just walk you through this. Okay, so we start going to 0 to 1, right? And so our entry time and our lowest time get initialized to the same value at first because when we haven't discovered the node yet, we don't know how if it could be any lower, so we just set it equal to the current entry time. Then we reach 2, it's going to get a value of 2. But what you're going to see here is we have something called a back edge, right? So a back edge is basically saying, is there an edge that points to an ancestor node in the DFS search, right? So as you can see, boom, the two is going back up the tree. In this case, it's not very relevant because there is no graph up here. But if we continue this, right? What we're gonna see is yes, low of 1. So when we see this back edge, right? What this is saying is there's two possibilities. If the back edge that we found to an ancestor in the tree is somewhere greater than the node itself, then that means there is an escape route. Let me explain. So look. Wonder if this actually doesn't illustrate that quite well. Okay. What we're trying to find is those nodes that separate separate two parts of the graph, right? Right, so we have that kind of shape right here, right? Connecting these two parts of the graph. So when we do our DFS, we need to, for any node that is along the DFS tree, so we have A, so we start with A, then we go to B, we go to C. Now, I'm going to add to this example because this example I realize doesn't actually illustrate that point. Let's say so we'll call this C and D. So I go from A, I go from B to C, A to B, B to C, and now I go. Let's say I go from C to A, which gives me this back edge, right? But if I instead go to D from C, and then take the path back to A, so right now C is the parent of D in the DFS tree, but because I have this back edge out to A, This tells me that C cannot possibly block D from a different node in the graph. I hope that makes sense. It's a bit vague, but you can see on the graph, right? If I were to take out C, right? D has no problem getting back into the rest of the graph, right? But let's say that instead we are talking about B, and we want to know, actually, does this take out B? When let's say we get to, let's continue on, right? So E, F, G. We unwind our DFS back to B because this is how DFS works, right? We explored this part of the subgraph. Now we're going to start exploring this part of the subgraph. So we're going to branch here. Now maybe this would be a better example for sure. So if we go to E, then F, then G, but now G goes back up to V, but no higher than, right? So what this tells us is that F and E, if we remove F and E, we can still make it from G back to the main graph. But if we remove B, because there's no escape hatch, there's no escape route to this part of the graph. See, if it were the case that G had a path to A, such as this, suddenly we know that B cannot possibly cut off G from the rest of the graph, and you can see that here, right? If we cut off B, we still have a path back to the rest of the graph. So the main idea of capturing the entry points and the low points is we're saying, look, low of G is A, right? In this example, the low of G is A. So we'll say low of G is A, and the entry time for B, so the Tn of B, okay, this is not gonna be here. So let's number these 0, 1, 2, 3, 4, 5, 6. Okay. The low of G is 0, but the time of entry is 1. So the Tarjan's articulation point method, the key thing that it checks every time is the relationship between this guy. If in this case the low is less than the time of entry of B, that means at some point in our DFS we were able to make it back to where we started before we got to B. In other words, we have an extra route out of that subgraph. Now, if instead we didn't have this edge, if instead G only simply went up to B, in other words, if low of G is greater than or equal to the time of entry of B, this tells us that there is no other way to get out of this subgraph without going through B. And that's the exact definition of an articulation, right? So this is the crux of the Tarjan's articulation point algorithm. We mark the entry time for each node that we visit, and if at any point the low value of G, in this case B, but in that previous case it was A, if it's higher than when we form a back edge, right? Because remember, we were going like this. We're only gonna check low and T, and if we form this back edge right here, right? This is the back edge. Once we form a back edge, we're going to compare the low of G, which in this case, we're going to be continuously updating the low of G by propagating the low down. So that's what you're seeing in the animation is every time we traverse a new node, right, we're going to update its low value. So 1, 1, 1, 1, 1. Does that make sense? We're propagating the low value down because That way we don't have to go back up and check, right? As long as we're keeping track of that low value, we can just say, okay, we have the low value of G, compare it to the time entry of B when we form the back edge. In this case, they're equal, so we know B is our articulation point. Okay, I'm just saying the same thing over and over again, basically. Does that make does you understand? Does that make sense?
Wait, is the values for low, are those integer values or are they referring to the nodes on the graph?
They are integer values.
Integer.
Yes, so what you're seeing here is, right, so what's going on at the beginning, right? We're going 0, 1, 2. So let me show you what's hidden on the animation. I realized it's not amazing. So what's secretly going on is when we do our DFS, right? We have the low value and we're propagating the low value down every time we do this DFS, right? So that when we eventually form a back edge, we're saying, which happens here, right? So when we finally hit that yellow edge, we've already visited 0, so we know it's a back edge. In the DFS tree, it looks like, wait, come on, there it is. In the DFS tree, it looks like that. So now we form the back edge, so we're comparing, okay, the earliest time I could have reached this node versus the back edge that it creates, what time is written there will tell me whether or not I can escape outside of beyond 0. In this case, it's trivial because 0 doesn't have any other subgraph. But imagine that there was a subgraph up here, then you know that 0 would be an articulation point from there, right? So let's continue on. The DFS, we hit 3, 5, 4, and then a back edge back to 1. So now what happens? So we have the back edge to 4, right? Our where's 4? 4 has a value of 5, but 1 has a value of 0. So we need to update the values of 4, 5, and 3 accordingly. So now what you can see is what the low value intuitively represents at a high level is it breaks the graph into these components, right? So as you can see, everything in the component that would be separated by 1 has a value of 0. Everything on the other side of 1 that would have been separated by 1 has a value of 1. And then what you're going to see is at the very end, 6, 7, 8. Now, 8 forms a back edge with 6. Its low value gets adjusted. 7 gets adjusted, and 6 gets adjusted. So now, here's where the check comes in. We're saying, okay, 7 and 8, they have no back edge to a value that is less than the value that 6 has. So therefore, 7 and 8 are trapped by the 6 node. And similarly for 3, 4, and 5. And 0 and 2 are trapped with 1. So these become articulation points. I think, okay, it's 6:36. I want to get to one problem first. So
Is 8 considered an articulation?
8 is not considered an articulation point because it does not have any subgraph that it's blocking. You could say like it's like trivially an articulation point because there isn't anything that it's blocking, right? if there was a node here that only connected to 8 or only connected to 7, then yes, it would be an articulation point. But what happens is in the DFS tree, we reach 6 first, so we know that it's just a property of the depth first search that lets you know that everything that you find afterwards, if the earliest you could have found it is no higher than its ancestor in the DFS tree, that means there's no escape. There's no escape.
When you say the earliest you could have found it, do you mean like the lowest number of parcels you would have had to take?
Exactly. That's why 7 and 8 get updated to the value of 6. Because if we're starting from 0, the earliest we could have found 8 and 7 is going to be well, the actual entry time is, like, I think about it like it's the lowest that you could have reached it, but it's not actually the lowest that you could have reached it, because it would have been 6 plus 1, right? 6 plus 1. But what you're basically setting it to is you're basically identifying the parent of this subtype. Like, you can consider if all of these nodes must go through this node, so they inherit its time value. Right? Because we're starting from here, we scan everything, we get to here. We could not have gotten to 8 or 7 before we had gone through 6. So therefore 7 and 8 inherit 6's value. If instead we had it edged from 2 to 8, then 8 would inherit 2's value, and we would say, okay, well 8's value is 0, that's less than 6, so therefore 6 is not an articulation point. Does that make sense? Okay. Again, like, I did not master this overnight. So, like, if you need to look at the animations, read the articles and stuff like that, please do. But this is like a very important algorithm, and it actually shows up in the problem that I want to go over. So let's switch gears to that. It's not this one. It's this one. So let's read through it. So you're gonna notice this sounds a lot like the TNT run that I mentioned, right? So you've landed yourself in a real mess, or more accurately, a cave filled with dilapidated and unstable pillars. Okay, you are luckily standing on a solid rock in the middle of the cave. You know that there's a valuable artifact on one of the pillars in the cave, but you aren't sure which one yet. While you wait for the results of a scan of the cave, you start building a robot to help you retrieve the artifact. The robot you build will be light, and it will assuredly be able to land and jump from any pillar at least once. To build the robot, you need to determine how powerful it needs to be in terms of its jump distance. If the robot is too weak, then it might not be able to reach a pillar, and if the robot is too strong, then it will cause a lot of damage when jumping and landing. Luckily, you've already mapped out where all the pillars are located with respect to your starting point at 0, 0. You don't know yet which pillar contains the artifact, and you need to finish building the robot before the first scan finishes. Given the locations of the pillars, you'd like to determine the smallest jump distance to guarantee that your robot can reach any pillar and return back to the start without landing on a pillar twice. So, you probably noticed, this is a very common trend in ICPZ, but all of this shit right here is just fluff, right? It's not, like, there's very few information in here that actually matters. I guess 0, 0 being your starting point is pretty important. But here's the crux of the problem. Given the location of the pillars, you'd like to determine the smallest jump distance to guarantee that your robot can reach any pillar and return back to the start without landing on a pillar twice. What does that sound like? Well, it sounds a lot like the TNT run, right? We can traverse these pillars, we can walk around, jump to each of these pillars, but we can't reuse any pillar that we went through, right? So what we're looking for is a kind of route throughout the graph, such that we can always get back to our safe rock as many times as we want. But we're trying to see, can I get to any of these? Can I get to all of the pillars? It doesn't have to be all in the same route, but I need to be able to get to all of the pillars without jumping on a pillar twice. So there's a bit of a layering here. That's the main idea, right? That sounds a lot like the articulation points that I was talking about, right? Because um, if there was an articulation point anywhere in that graph, then you know for a fact that you can't come back. You can't. That's a weakness in the graph. You cannot hit the nodes in the subgraph that are trapped by that articulation point. Okay. So that's the first step. The second idea, and that's the second idea I want to go over, is the idea of the jump distance. And I have power in my code, but so let's take a look at the inputs. So the first line of input is a single integer n, which is the number of pillars. So we can have up to 1,000 pillars. Now again, think. Would they ask me for Hamiltonian cycles with n of 1,000? Well, that would be 2 to the power of 1,000, which blows up so ridiculously fast. They're never going to ask you for something that is NP hard in that amount of time. Okay, so each of the next n lines contains two integers, x and y, which are the coordinates of each pillar. All the pillars are distinct and no pillar will be at 0, 0. Output a single number, which is the minimum jump distance needed to guarantee that a robot could reach any pillar and return back to your starting point without landing on a pillar twice. Your answer will be accepted if it has an absolute or relative error of at most 10 to the minus 6. So how are we going to do this, okay? Well, first we need to build the graph, right? So if we're just getting a list of points from 0, 0, right? So we have 0, 0. We could have a point here at negative 10, negative 5, something. We could have a point here at 5, 0, 5, or 5, 0, I mean, right? Etc. We get to choose how big of a jump. So the robot can always jump less than its max distance, right? So obviously we're never going to overshoot a pillar, but we need to make sure that we can reach all the pillars, right? So we need to we're trying to balance two things, right? Because it wants the shortest jump distance. If it didn't ask for the shortest jump distance, right? We could just, let's say we have a guy over here, right? We don't need to worry about articulation points because we can just jump from here to here to here, and then just jump all the way back to safety without caring about having to traverse any of the pillars again. But we want the shortest distance that lets us do this. So, in order to build the graph, we need to basically build the graph on the fly. What we're going to do is we're going to say, okay, let's say I'm here. For all of the graphs, for all of the nodes in the graph, whichever ones are within my jump distance, I'm going to add them to my search. Okay? Everything that's not within the jump distance, I can't add to the search until I get close enough to add it to the search. Okay? So that's how we're going to build this graph on the
So
fly.
are you starting out with an assumed jump distance and then changing that as you go?
That's correct. You have to because I mean, you could start at 0, I guess, and then just go up until you reach something like that. But we're working with real numbers, right? So how do you linear scan over the real numbers up to 10 to the minus 6 accuracy, right? So you need to do increments of 10 to the minus 6 from 0 to who knows how long. Well, actually, we do know how long. We know that the maximum distance that you'll ever have to jump has got to do with that x and y bound, right? What is the x and y bound? Well, the maximum distance you could possibly have, right, would be if you had something in the bottom corner, negative a billion, to positive a billion, right? So if you remember Pythagorean theorem, right, the shortest distance between two lines, in the worst case, you're going to have to do this jump. So, the distance is what? So, you do 2 times, the distance is positive 10, positive a billion minus negative a billion. So that's just 2 times a billion squared plus 2 times a billion squared. Right? So you get 4 times 10 to the 18 plus 4 times 10 to the 18, etc. You get the point. I'm not going to do all that. But we have an upper bound for the distance. So you will see this a lot. This is a common trick if you didn't know. If you haven't seen this before already. But instead of a linear scan, right? I'm just going to review it. I don't know. Make it, but if we're trying to do a linear scan over the reals, right, that's going to take too long. But the reals are sorted, right? We're looking from 0 to this huge number, right? But we're trying to find some number in here such that it's the minimum feasible real number, that minimum feasible jump distance, right? So what is a cool algorithm that we can use over a sorted list of numbers to find a specific point in those numbers? The key word is that it's sorted, right? The main idea is that we can use a binary search. Have you heard of binary search? Binary search. Yeah, so a binary search.
Sorry, go ahead.
No, you go ahead.
Is it like when you divide it into half because it's sorted, so you can only make half?
Absolutely, that's exactly right. So instead of going from 0 to this big ass number like this, let's just start in the middle. We check. We do our articulation check. If we're able to, if we're not able to get back to the end, right? First of all, there's one other property, right? The bigger the jump distance is, right, the easier it is to get to the start, because remember, we can always jump directly from anywhere back to the start if our jump distance is big enough, right? So it's never going to be such that, okay, if I make let's say I could make it, but I could make it from here, but the jump distance is too big. It's never going to be such that if I increase the jump distance, I suddenly can't make it anymore. So this is called a monotone predicate, and it's basically saying everything to the right will always be checked, will always satisfy, but everything to the left, we don't know yet. So we cut in half, we cut our jump distance in half. If this is a check, then we're going to keep cutting down in half. If it's an X, we know that our jump distance is too small now. So we're going to continue the binary search up here, like this. X, check, X, check, until we finally get to this perfect value in the middle, which will be our optimal jump distance, right? This will give us the minimum feasible jump distance without having to do a linear scan over the real numbers. So this is called binary search over density, which is a very common pattern. I've used it plenty of times to find, you can use binary search to find the optimum points on a graph. You can use it to find the roots of a polynomial. If you heard of gradient descent, binary search also works similar to gradient descent on sorted numbers. Okay, so that's it. That's the main idea, right? So we're going to just check, do Tarjan's articulation point check. If it works, then we're going to try something lower. We're going to keep trying lower distances until it doesn't work anymore. And we're going to single in on that value that minimizes that jump distance, but still allows us to complete it. So let's take a look. Actually, we don't have enough time to go over all of this stuff, but you can look over, this is Tarjan's right here. This is Tarjan's algorithm. We're checking, remember the low I call it discovery disk instead of Tn, but it's the same thing. So this is our back edge, right? And here is our distance. It's the distance squared because we don't want to do square roots because that's slow. You just check the distance squared time if it's greater than the jump power squared, right? P is the jump power. So if our distance between any of two nodes is greater than the jump distance, then we ignore it, right? But if it's less, then we continue with Tarjan's check, right? Okay. And then this checks for connectedness. So this is optional, but nice. Basically, if I can't, let's say there's a node that isn't connected in the graph, right? There could be an edge case where I just have a graph and then some guy over here. That's okay. I don't want to waste time doing all of Tarjan's algorithm if I know for a fact that I'll never be able to get to this node. So I can just turn false early. So that's what the connected check is for. We do the connected check. And here's the binary search. You might want to pay attention to this, right? So this is the value. This is the highest that it can be, right? I got that value just by doing by hand the distance formula between the large thing. And then low is 0 because you can't jump you can't jump negative amounts. And then so what epsilon is a common pattern. You see this in machine learning a lot. Epsilon is the small value that we are acceptable having some kind of error, right? Because we can't, the binary search, first of all, the problem statement says we only need to be at 10 to the 6, 10 to the minus 6 close to the answer, right? So if we're off by 10 to the minus 7, it's no big deal. So I just did 10 to the minus 9 because I was nervous about making it exactly 10 to the minus 6. But if you do it any lower, like 10 to the minus 18 or something, you're gonna have a time limit exception because you're gonna be going so far into the details that you don't need. It's gonna take too long to complete it in time. So the basic idea is, so while remember the binary search holds a high pointer, a low pointer, and a mid pointer. So what we do is we take the midpoint while the difference is greater than the epsilon, right? Because if it was less than or equal to the epsilon, we've centered in on our value, and that's good enough. Okay. Otherwise, we take the midpoint. This is a standard library function. It just literally does this: low plus high minus low. It just does that. It's just the average, right? It's just the average point, the midpoint. If OK of mid, remember OK is the Tarjan's check plus the connected check, right? So if we have if we have OK of mid, which just means were we able to complete the objective at this jump distance, then we're going to try a lower power, okay? Otherwise, if it wasn't, then we're going to try a higher power by doing our binary search. We're cutting it in half every time, right? And so this total algorithm, right, we're doing log of n for binary searches, log of n. The OK, if the graph is connected, then it's just a single DFS, right? And the DFS is linear in terms of the number of vertices and edges, right? So we're going to basically have n log n as our answer, which is acceptable for this time requirement. Remember, if we go back to week 1, we can check our time requirements. N log n is for about 100,000. So we are within that distance for let's see, 1,000 times. Well, I don't want to do the math. It doesn't time out because it is a fast enough algorithm. So okay, we've got 4 minutes left. I want to show you this last video that I made for the other problem. We're not going to go over the solution, but basically the idea is it's chess. So you have a rook and you have a target, okay? And you have a bunch of stationary knights on the board who are blocking your path, right? So this is all of the squares that the knights are attacking, Okay? And you're asking, can I get to the target? Is it reachable? What you can do is if a knight is not defended, you can take the knight, right? Those are standard chess rules. If you can take the knight, you can take it. And when you take the knight, all of its attacked squares, right? If you don't know, the knight attacks in an it attacks in 8 directions, all in an L shape from its center point. So like, look, it's really fast, but like this knight right here is going to hit this square, this square, this square, this square, this square, this square, and this square, and this square. If I didn't say that right, that's what that knight's going to do, and they're all going to do that, and it makes this grid. So the rook can't pass this way because there's a knight and it's protected. It can't hop over the knight, right? But it can take this knight. So we're trying to ask, okay, what combination of moves do I need to do so I can get to the target? And is it possible? So what we're going to do is we're going to start at our rook, and we're going to do a breadth first search, okay? So we're going to scan. It scans right. It hits the knight. You can't go that way. It scans up. It hits the other knight. We can go that way. So we're going to add it to the queue. There's nothing else to do, so we're going to pop it from the queue and travel there. Consume the knight. When we consume the knight, we're going to start deleting the squares that it was attacking. If this square hits 0, what we need to do now is we need to make sure that we got to check if we can reach that square now, right? How do you do that? Well, we're going to scan up, down, left, right, and try to find any other reachable square. In this case, it's not going to find anything because there's no up, down, left, or right path that is going to get us to any of those blue squares, right? So we're going to leave that alone. None of the other attacked, when we remove the knight, none of the other attacked squares hit 0, so we're going to just move on. So remember, the rook can move over an attacked square, it just can't land in an attacked square. So we can go over that red 2 up here to 1, 0, 1, 0. And also, breadth first search scans to the right as well. It finds the knight, and it adds that to the queue. Now, it's a breadth first search, so we're going to start with the top guy. He goes this way, and he scans, and he finds nothing that he can do. So, right, because he either hits the edge of the board, or he hits that knight on that square to the right. So now we go back, we pop off the knight, now we consume this knight, and now watch this. We're going to remove that guy. So that guy goes to 0. We're going to scan, and it's not going to be able to hit anything that we've already reached. Not going to be able to hit a blue square going up, down, left, or right. It either hits a knight or an edge of the board. But what happened really fast is you see that one in the bottom left, that one that just flipped from red to black. We're going to scan up. Boom, and we find this square, which is reachable from the rook, because if you look if you look at that node from from the beginning spot, right? We now have a way to get from the original rook starting position up to here. So what we've encoded is basically this path. So we go up here, back down to here now that it's opened up, and then back up here, right? So that's every time we free up a square, we do this like expansive scan to make sure that we can reach this new point. We add it to the queue, and it's going to, we add it to the queue, but we still have to remove the rest of that knight's attack squares that we got. So we're going to do that, and it's going to find that square, because we also freed up the knight itself, right? So it's going to find this square below. And now we pop from this point, and now, as you can see, it's just a straight line to the target. So what we've basically encoded. So we've encoded this path, right? Boom, 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 boom. But we didn't have to do all of this recursion or anything like that, because we encoded this smart scan, which every time we free up a square, we just expand out like that. So that's this problem is literally just a BFS plus more BFS, like sub BFSs inside of BFSs. So Give this one a try. Try to code this because it's just BFSs and if conditions. And but it is tricky because there's a lot to do, right? So this is another kind of ICPC problem that you're gonna see. Something like that. Is there anything else I wanted to show you? Yeah, we don't have time, but I'll upload these as well. These topological directed acyclic graph algorithms are very important because they encode relationships. So for example, one of the problems that I did at ICPC was A wants to be on a team with B, but C doesn't want to be on a team with either of them, but D wants to be on a team with D. So like, how do we make the team such that everyone is happy, right? Well, that's a graph problem because now I can draw these directed arrows to who likes who and who doesn't like who and whatever. And then I can do graph shit on them. So, for example, if I wanted to find, well, there's a lot of different things we can do, but in order to do them, you need to first learn how to topologically sort, which that's what this goes over. I'll upload that algorithm. And then there's also the, you can, once you have it sorted, you can find the shortest path in linear time, the longest path in linear time, and the number of paths in linear time, which are all, they show up in some of the problems that I have linked in the announcement. But that's all, guys. Did you have any questions or anything else you wanted me to talk about or show you guys? That's pretty much all I have that can fit in the time. So if not, then thank you guys for showing up. And I'll see you guys next week.